Today let us talk about the kinematics of circular motion, which is another type of motion in a plane, right? It's a two-dimensional motion. Let us understand the terms and the aspects associated with a circular motion. So, what is circular motion? Circular motion is when a body moves along a circle, simply said, right? So, let us say this is a circle about which there is a body moving, and what we can do in the process of studying this circular motion is we can consider the center of this circle at the origin of our Cartesian coordinate system. So that it is easy for us to mathematically understand the motion. Okay. So, let us say this is the circle along which a body is moving at any point. Let us say the body is at a position P on the circle. Then we understand that the distance from the origin to the point P would be nothing but the radius of the circle, right? And then we can define something that we call as the radius vector or the position vector, which would be a vector pointing from the center of the circle to the point P, the position of the particle. So, it will be either the radius vector or the position vector of the body which is at the point P. And we also define the angle that this body has covered, assuming that let us say the body started off from the x axis from the point A, and having travelled a certain distance along the circular path, at the center it has subtended an angle theta. In that case, we call this angle theta as the angular displacement of the body, angular displacement, which by convention is always measured in the anti-clockwise direction. So, we start from the positive x axis and we go anti-clockwise to measure the angle theta. Understand that vector r here can be called as the radius vector or the position vector of the particle. Now, what we try to do is we try to write this vector r in terms of its components along the x and the y axis. So, what we do is we draw perpendiculars from the tip of the vector onto the x axis. We see that this length here will be nothing but the component of vector r along the x axis, which mathematically would be r cos theta from trigonometry. And similarly, the component along the y axis, which will be of this length, will be called ry, and mathematically it will be r sin theta. So, from our information of vectors, we can say that the position vector r of this particle at any point in time can be written as rx I cap plus ry j cap, right, which after substituting the values of rx and ry would become r cos theta I cap plus r sin theta j cap, isn't it? Now, see what can this be written as further. We can take the r common and we can write this as cos theta I cap plus sin theta j cap, right. This is your vector r. Now, we know that in general a vector, any vector, which in this case is vector r, can be written as the magnitude of the vector times its unit vector, right. We know that in general vector a can be written as magnitude of a times a cap. The magnitude gives us the magnitude of the vector itself, and the unit vector gives its direction. So, the two combined together gives us the complete information about the vector. So, if we compare this relation with the expression for r that we have obtained over here, we understand that from here the unit vector r would be nothing but cos theta I cap plus sin theta j cap. We can check mathematically that this vector indeed has a magnitude of unity. The magnitude of this vector will be square root of cos squared theta plus sin squared theta, which we know is always 1 for any value of theta. This is always 1. So, this is indeed a unit vector, right. So, this is giving us the direction of vector r. And as we look at the figure, what is the direction of vector r? It is pointing in the radially outward direction, right. From the center, it is pointing towards the position of the point P, the body, the position of the body which is moving in the circular path. So, can we say this vector unit vector r essentially is pointing in the radial direction, radially outward direction. Yes. So in terms of the unit vector r and the magnitude of r, this is how we can write our position vector r. Now we can go further and try and find out the velocity of this particle p as it moves in the circular path, right? And for that, what we shall do is we shall simply differentiate the position vector. So in general, we can write that the velocity vector v can be written as the rate at which the position vector r changes with respect to time. This would be the usual definition of the velocity, right? Now, if we want to differentiate or find out the rate of change of vector r, it would mean we are supposed to find out the rate of change of the vector r as it is written above is r cos theta I cap plus r sin theta j cap, where we know r is a constant. The radius of the circle in which the particle is moving is actually a constant. What varies in this expression is the angle theta, right? As the particle moves, we know that the angle theta changes, it increases with time. So it is essentially theta that is the changing quantity here. So we can take the constant r outside and we say that we are essentially supposed to differentiate the term theta, but we are supposed to differentiate with respect to time. So see that the variable with respect to which we differentiate is different from the variable which is being differentiated, theta. So what do we do in that case? The differentiation of cos theta, which will be minus sin theta, we shall write that. But then along with that, since we are differentiating with respect to t and not theta, we have an extra term of d theta by dt coming in. This comes from our knowledge of rules of differentiation, right? When we are differentiating with respect to a different variable, this is how we manage it. Plus the second term would be, we have already taken an r outside, so differentiation of sin theta, which will be a cos theta, into once again d theta by dt into j cap. This is what we shall get upon differentiating the expression. And now what is this quantity here, d theta by dt? Do you see that d theta by dt, as the expression itself is, it is the rate at which the angle theta changes. Theta we have defined as the angular displacement. So the rate at which the angular displacement changes with time, d theta by dt, we call it omega, the angular velocity. Angular velocity is the rate at which the angular displacement changes with respect to time. Okay? And this omega now we can take out. So velocity vector v would become, this becomes omega, and this term here also is a omega. So we can take omega out, and this then becomes r omega into minus sin theta I cap plus cos theta j cap. This is what we get as our velocity vector, right? Now look at a few more things here carefully. Just as we have done with the radius vector r, can we say in general the velocity vector v can also be written as the magnitude of v times the unit vector v, right? So when we compare this relation with the relation that we have just now obtained, do we see that this term that we are getting here within the bracket, it is a unit vector. See for yourself, this has a magnitude of 1. How? Because when you try to take the magnitude, you will get a minus sin squared theta, which will become sin squared theta, plus a cos squared theta, which will once again be 1. So this is also a unit vector. So this becomes our v cap, the unit vector corresponding to the direction of the velocity, and then this particular term that we are getting outside the bracket should be the magnitude of velocity, isn't it? So when we compare the two, what we get is the magnitude of the velocity, or we can also call it the speed with which the particle is moving, is nothing but r into omega, the radius of the circular path times the angular velocity of the particle. This is an important expression. We also get the magnitude, the unit vector v, the direction of the velocity vector, as minus sin theta I cap plus cos theta j cap. in a while we shall try to find out the direction, we shall try to see what exactly this direction is in terms of the figure. Okay. So, this relation in that sense becomes another important relation. Let us rewrite it. Velocity vector v is r omega into minus sin theta I cap plus cos theta j cap, an important relation in circular motion. Okay. Now, in order to understand what the direction of this vector is, what we do is we try to find out the dot product of vector r with vector v. We have the vector r with us as r cos theta I cap plus r sin theta j cap, right? And we also have the velocity vector with us. If we just take the terms inside, we will have minus r omega sin theta I cap plus r omega cos theta j cap, right? These are the two vectors. Let us try and find out the dot product of vector r with vector v and see what we get. So, by using the relation a dot b is equal to ax bx plus ay by, here we will have r cos theta times minus r omega sin theta, which will be minus r squared omega into sin theta cos theta plus ay by, which will be r sin theta into r omega cos theta, which will give us r squared omega into sin theta cos theta. This comes directly from the formula for dot product. And if we look at it carefully, the two terms are exactly the same, just that one is with a minus sign. So, the two will cancel out and we will get the result as 0. The dot product of vector r with vector v is coming out to be 0. What does that imply? That implies that the vector r is perpendicular to vector v, because their dot product is coming out to be 0. This is the result that we get. Now, what is the meaning of vector r being perpendicular to vector v? This means that the velocity vector is perpendicular to the radial vector, radius vector, that is. How do we see that? If this is the center and this is the radius vector at any point in time, the vector r, so that the position of the particle is over here at the point P, then its velocity vector will point along the tangent drawn to this radius vector. Do we understand that the perpendicular vector to vector r will be a tangential vector? So, from there we understand that the velocity vector is actually along the tangent to the circular path. And that also makes us understand that the unit vector v that we have written above, which was minus sin theta I cap plus cos theta j cap, this vector is actually pointing in the tangential direction. So, it is a tangential vector, or along tangential direction it points, right. So, what we understand here is that the radius vector points along the radially outward direction, vector r cap, and the velocity vector of a particle moving in a circular path is always along the tangent drawn to the point where the particle is at any point in time. Both of these informations are important. So, in these terms now, what we shall do next is we shall try to find out the acceleration of this particle. But to find out the acceleration, we shall be covering it in two different cases. One case would be when the particle moves in a uniform circular motion. We shall define what we mean by that, and then a non-uniform circular motion. Okay. So, the next exercise would be to find out the acceleration, for which we now divide it into two parts, the whole thing. Case 1 is a uniform circular motion. As the name suggests, uniform circular motion means when the particle moves on the circular path uniformly. What does that mean? That means that it moves with a constant speed. V is a constant. The speed of the particle does not change, so that it covers equal angles and equal intervals of time. Now, we know that V is also equal to r omega, isn't it? So, that means r omega is also a constant. Out of r and omega, r anyway is a constant. The radius of the circular path is never changing. That means omega is also a constant, right? Omega, which we know as d theta by dt, the rate at which the angle changes, that's a constant, right? So the angle theta changes at a constant rate. Equal angles are covered in equal intervals of time. Okay. So from here now, if we try to find out the acceleration, we start with our velocity expression, which we have already obtained above, r omega into minus sin theta I cap plus cos theta j cap. And now what we do is, in order to find out the acceleration, we differentiate it. That's how acceleration is defined, right? The rate of change of velocity gives us acceleration. Rate of change of velocity means, look at the expression above. Out of the whole expression for v that we have, r and omega now both are constants for a uniform circular motion. So we are only supposed to differentiate this particular expression where the only variable is theta, right? So we'll keep r omega outside and we shall do d by dt of minus sin theta I cap plus cos theta j cap. This thing we have done above also, so we shall see how we get it. So we differentiate sin theta first, we'll get a minus cos theta, but then since we are differentiating with respect to t, we have to put a d theta by dt I cap plus differentiation of cos theta is minus sin theta, and then once again d theta by dt j cap, right? Once again, see that we are getting extra terms of d theta by dt, both of which are omega. We can take this omega common out of the expression, so that we get r omega squared into minus cos theta I cap minus sin theta j cap. This is what we are getting for vector A. Now, if you look at this expression carefully, this is once again a unit vector. In fact, if we can recall, the unit vector r, the radial vector, was given by cos theta I cap plus sin theta j cap. So what we are getting here is just the negative of that, isn't it so? This is just the negative of the radial vector r. So can we write it as r omega squared into minus r cap, right? Now this minus r cap essentially is telling us that the direction of this vector A that we have obtained here, the acceleration vector, is just opposite to the radially outward direction. Vector r cap is pointing in the radially outward direction. So what will be the direction of minus r cap? It will be in the radially inward direction, right? So this acceleration that we have obtained here points in the radially inward direction, and it has a magnitude of r omega squared. This is the magnitude, right? So this acceleration that acts on a particle which moves in a circular path with a constant speed, that means the particle moves in a uniform circular motion, this particular acceleration is called centripetal acceleration because of the nature that it has, pointing in the radially inward direction. So centripetal acceleration, if you want to see this, this is how it acts. If this is the circular path, then if the particle at any point is at a position P, let us say, then the centripetal acceleration will act radially inward, and since we are calling it a centripetal acceleration, we now write it as A with a subscript C, AC. So we can write the vector AC now as r omega squared into minus r cap. This is the magnitude, so we can write magnitude of AC is r omega squared, and the direction of the acceleration, centripetal acceleration, is in the opposite direction to the radially outward direction, that's the radial inward direction, right? So this is a very important term that we have understood about uniform circular motion, this concept of centripetal acceleration. This is, understand that centripetal acceleration would be the one that creates a change in the direction of the velocity of the particle. Why? Because we know that its magnitude is not changing. The particle which is moving with a constant speed, the magnitude of its velocity is not changing. What it's constantly changing is the direction of velocity. So the centripetal acceleration creates a change in the direction of the velocity of the particle. It does not create any change in the magnitude of its velocity, right? So this is about the centripetal acceleration. See that this relation r omega squared that we have written for magnitude of centripetal acceleration, knowing that v is equal to r omega, we can write r omega squared as r into v by r whole squared, because omega can be written as v by r, and from here we can write this as v squared by r. So there is another formula that we give to the magnitude of centripetal acceleration, which is v squared by r, which is the more known formula. Actually, it's used more in the questions, in the applications of it. So we have got two magnitudes, like two formulae for the magnitude of centripetal acceleration. One is r omega squared and the other is v squared by r, where v is the speed of the particle, right? So next we come to a non-uniform circular motion, the one in which the particle does not move with a constant speed. Non-uniform circular motion, where now we understand that v is not a constant, right? V is no more a constant, that means omega is no more a constant, right? So before we start working on this, we now define a new quantity that we call as the rate of change of omega. Now that we know that omega is changing with time, there would be a rate at which it changes, right? So this rate of change of omega is now named a special, now it's given a special name, we call it alpha, the angular acceleration. Angular acceleration, right? It plays the same role as acceleration plays in linear motion. Here this alpha plays the same role as that of acceleration in circular motion, okay? So having defined this, let's get back to the velocity expression that we have already obtained with us, r omega into minus sine theta I cap plus cos theta j cap. And now when we try to differentiate it to find out the acceleration, vector A, which will be dv by dt, understand that it would now mean that we have to differentiate two terms. One is omega and the other is this expression. Both contains the variable r. Omega and theta both are variables this time. So what we do is we put r outside, which is still a constant, and we write d by dt of omega into minus sine theta I cap plus cos theta j cap. So how do we differentiate this whole expression now? We consider this as the first function, this as the second function, and we use the formula that we have, or the rule that we have in differentiation when we try to differentiate two functions given in product form, the product formula, the product rule, which says that we keep it's the first function into differentiation of second plus the second function into differentiation of the first, right? So this is what we use now. So this gives us r into first function omega into differentiation of the second, which would give us minus cos theta into d theta by dt I cap minus sine theta into d theta by dt j cap, right? Plus the second function into the differentiation of the first. Omega's differentiation will be d omega by dt. So this is what we are getting as our complete expression upon differentiation. Now if we look at it carefully, we are getting d theta by dt over here, which we can take out as omega. So we'll get an omega squared over here. Take r inside. So as we get r into omega squared into minus cos theta I cap minus sine theta j cap, which is actually the same expression that we have obtained earlier also when we were discussing the uniform circular motion, right? This term that we have got is nothing but the centripetal acceleration. Plus this time we have got another term. So when we take r inside, and this d omega by dt becomes alpha, we will have r alpha into minus sine theta I cap plus cos theta j cap. So if we look at this whole expression, we see that it consists of two terms. This is one term and this is the other term. See that the first term is the same as the centripetal acceleration AC, which is equal to r omega squared in magnitude, and its direction is in the radially inward direction minus r cap. Whereas when you look at the second term, this term r alpha is the magnitude of the second type of acceleration that we are getting here, whereas this unit vector that we see is the same as the unit vector unit vector v, that is along the tangential direction, right. So this second term that we are getting here is the second type of acceleration that the same particle would have, which is such that it points along the direction of the velocity, which is nothing but the tangential direction, and hence we give this acceleration a name tangential acceleration. We write it as AT, and this tangential acceleration has a magnitude of r alpha and it points along the tangential direction, which is along the velocity vector, right. So now we can express our vector A in terms of the centripetal acceleration AC plus the tangential acceleration AT, where the centripetal acceleration is given by r omega squared into minus r cap, plus the tangential acceleration is given by r alpha into v cap. A very important relation for us to use into questions. Let us look at it in a figure also. How is this thing really working out? So let's say this is the circular path in which the particle is moving. The particle right now is at the position B. Do we understand that the centripetal acceleration of the particle will be acting along the center, towards the center, that is. So this is AC, the centripetal acceleration. And at the same time, this tangential acceleration will be acting along the tangent, which is this. Now from the figure, do we understand that these two accelerations are perpendicular to each other, right? And if we try to find out the net acceleration vector, we have to take their vector sum like this. The vector sum of the two acceleration, which will be the net acceleration vector A, will come out in this direction, and we can easily find out the magnitude of vector A. Now that we know that the two acceleration vectors AC and AT are perpendicular to each other, we can say that the magnitude of vector A would be given by nothing but the Pythagoras theorem. We can say that it will be AC squared plus AT squared, right? Very important relation here. And we can also find out the angle, let's say, that vector A, the net acceleration vector, makes with any of the two accelerations, component accelerations. Let's say theta is the angle that the vector A makes with the centripetal acceleration, let's say. Then from the same figure, can we write tan theta is equal to, for this particular triangle here, the opposite by the base, which will be AT by AC. So see that this way we can find out both the magnitude as well as the direction of the net acceleration vector of this particle which is moving in a uniform circular motion, and we can also find out the individual accelerations, the centripetal acceleration, which is responsible for bringing in the change in the direction of the velocity vector, and the tangential acceleration, which I hope you all understand now. Tangential acceleration is the one that brings in a change in the magnitude of the velocity of the particle. In fact, if we just look at this a little more in detail, the tangential acceleration, whose magnitude we have obtained as r alpha. See that alpha, the way we have defined it, is d omega by dt, the rate at which the angular velocity changes. If we take this r inside, we can also write this expression as d by dt of r omega, right? And what is r omega? R omega is nothing but v, the speed of the particle. So this is nothing but the dv by dt, the rate of change of the speed of the particle. Mind you, v here is not the velocity, it's the speed. So this is the rate of change of speed of the particle, which is giving us the tangential acceleration. So it's a tangential acceleration which is responsible for bringing in the change in the speed of the body or the magnitude of velocity. Okay.